objective today is that we're going to learn about stars and HR diagrams. And your essential question, so what you should be able to answer by the end of this period is how do you compare and contrast stars using HR diagrams? Which basically means you need to understand what stars are, the differences in the different stars, and then we're going to look at an HR diagram and how those stars are plotted on that HR diagram, and how that diagram gives you information about the stars. Okay? So, to start off, we're going to look at the composition of stars. All stars are primarily hydrogen and helium. Depending on what part of the life cycle they're on, then they have more one than the other. Okay? The younger stars have hydrogen in them, for the most part. The older stars have helium. And the reason the older stars have helium is because they've already burned off all the hydrogen. Okay? Remember when we talked about the Big Bang Theory last week, I said that one of the evidence of us knowing that about, or thinking that the Big Bang is true, or evidence that supports the Big Bang, is that they found helium in the outskirts of the universe, right? Okay? And we said, well, it makes sense. If those are the most simplest elements, then they should be the most oldest elements, then they should be out in the outskirts, for the most part, because everything went from the inside out, right? So, stars were made by those elements, basically are primarily those elements. Questions, Lee?
On the notebook, are we skipping a few pages, or do I just not have some of the stuff?
Well, you might not have all the stuff, because the stuff that we did last week, because like, the last thing that we did together was page 81, right? Page 82 was the Hello ET, which was where your location in the universe, you're talking to an extraterrestrial. Page 83 was, what is our location in the universe? Page 84 was the galaxy potable. Page 85 is how are the galaxies classified. Those are things that you did Thursday and Friday, correct? Y'all put them in those right places, right?
Yeah.
Okay. Page 86 we're going to do today, and page 87 you're done. So, did that catch you up?
Yeah, I just had to come in Sunday and get out of it.
Okay. Alright, so when we're looking at stars, basically we're looking at hydrogen and helium. So, remember that when we look at the periodic table, there's several things that we have to remember about it. Okay, hydrogen and helium, you need to remember that they're the primary elements in stars. Okay, so remember CHOPS?
Yeah.
Those are what? Elements with what?
Organic.
In humans, organic compounds, right? So CHOPS, elements in organic compounds. Now H and HE, elements in stars. So it's one more thing that you need to remember. So remember when I told you that you want to put some stuff on the periodic table as soon as before you take a test, that would be something else that you would do. I would probably draw a star on H and a star on HE to remind me that those are the elements in stars. Okay? Alright, now, when we look at size of stars, size are related to density. And how do we calculate density again? Mass divided by volume. Okay? So density equals mass divided by volume. A large size is equal to a low density. So a large size is equal to low density. So what can you tell me in regards to the mass compared to a volume of a large size? A large size relates to mass or volume? A large size. I take more space, so that's what? Volume. So a large volume, you get a low density. So mass is equal, density is equal to mass divided by volume, and the volume is big. In order to have a low density, what does my mass have to be? Little or big? Little, right? If I have a volume of 10 and I need a low density, wouldn't it have to be a smaller number at the top? Yes, I would get a decimal, correct? So, when we think of large stars, the bigger the star is, it's actually a low density because even though it's humongous in volume, the mass is little because it's big because of the gases that are being swollen. It's not very dense, meaning that things aren't very stuck together. All right? A small size is a high density. Now, our sun, which these are important, you need to make sure that you understand size, brightness, and different things about our sun. Our sun is an average size star. So it's not the biggest, it's not the smallest, it's medium. Okay? So our sun is medium. So I would put a star beside anything that we write about our sun, because you need to know that. Okay? Now, when we think of color and temperature, we talked about color and temperature when we talked about the periodic table, and I said, remember we drew that little color chart, and I said blue and red, and I talked about which one is high melting point, low melting point, and when I drew it, it kind of looked like it was backwards, and I said I'm doing it this way because we're going to talk about stars. This is what we're going to talk about. Okay? Usually when we think of a red color, we think of hot. Because when we turn on the faucet, isn't it red whenever we want to turn hot water? Okay? But in science, when we look at actual colors, it's backwards. Hot is blue. Red is cool. Now it's still hot compared to us and things like that, but it's the coolest one. So when we look at colors and temperature, red and orange are our coolest temperature stars. Blue and white are our hottest temperature stars. Okay? That's important. You need to make sure you remember. So red and orange, coolest temperature. Blue and white, hottest temperature. So basically, you're going to have to kind of think backwards of what you usually think when you think of the faucets and things like that. Because you tend to think of reds as your hot colors, but they're actually, when we talk about stars and heat, they're the coolest. And blue would be the hottest. Our sun is yellow. I hope you know that because I'm sure you've seen the sun. And yellow is an average temperature star. Okay, once again, I would star that. You need to know that. All right? Up to this point, are there any questions?
So our sun is like our average.
Yeah, basically our sun is average. And we're going to see why it's average in just a second. So then we think of brightness. When you go outside and you look at the stars, are they all the same brightness? No, some twinkle a little brighter than others, right? All right. And brightness can be related to several things. Brightness can depend on the size, the temperature, and the distance from the observer. That makes sense. If you're outside and the lights of the stadium are on, do we have lights on the stadium?
No, but in the parking lot.
Okay, the parking lot. Let's say those. Those are pretty big, right? If you're over here in the park, can you see those lights if those are on? They look pretty bright, right? Now, what if I was over there and I had a flashlight and I turned on the flashlight? Would you be able to see that flashlight with the same intensity as those big lights in the parking lot? No, right? You don't be able to see them because isn't it smaller? So the brightness depends on size. Now, what if I had that same flashlight and I was over here right in your face? Would it be brighter? So now that brightness doesn't depend on size. It depended on the fact that I'm closer to you, correct?
So this is distance?
Distance can also be a dependent. All right? And temperature. With stars, obviously, if they're hotter, wouldn't they be brighter?
Yes.
It kind of makes sense, right? So when we think of brightness, it depends on a variety of things, not just one thing. And the reason is because of the different instances that it occurs. Okay? Now, but for the most part, when we think of color, the blue-white stars are the brightest because what temperature do they have? They're the hottest. So because they're the hottest, they tend to be the brightest. And the reds are the dimmest. Our sun is average temperature, I'm gonna move this for a second, because I need it closer. Okay. Our sun, for the most part, is of average brightness. So when we really think about a sun, we can just think of it as average. Average size, average temperature, average brightness. It's sort of in the middle. Okay? And we're gonna see why in just a second when we look at the HR diagram. Yes?
So why don't we see like blue and red?
Why don't you see?
Yeah.
You actually do. You never, and it's hard to see it here. If you ever see a very clear sky, you will see that some of the stars look a little, not blue, but have a little more blue tint, and you can see stars that are a little more red tint. You can see it a lot better, obviously, with a telescope and things like that. But also, you have to think about that they're really far away. That light traveled hundreds of years sometimes. So because the brightness isn't as bright, you're not going to be able to see the color very clearly. But if you have a very good telescope, you can actually see the tints.
What about green?
I'm sorry?
Is green a color?
I'm pretty sure yes, green is a
Well, that color is
for the stars. Is green on there? Nope, green's not a color. But you will always have a tint. You can see a tint just because of colors changing from wavelengths from one to the next. Yes.
So, on the colors, do they vary it from red to blue? Okay.
Yes. And we're going to look at the specific colors in just a second. All right. All right. So when we talk about brightness, the other word that you might encounter is magnitude. Please make sure you put a star by that. Know that the word magnitude is a synonym to brightness, because you never know which word they're going to use. Okay? They could use brightness, they could use magnitude. Alright? So overall, that's what you need to know about stars. Now, our essential question is to compare and contrast stars using an HR diagram. So that's information you need to know about the stars. And now we're going to look at them as how do they relate into an HR diagram, which basically is just a graph that shows you the different stars. And they're put on a graph for you. So you don't have to copy this. You're going to get one in just a second. I just want to show you what we're talking about. That is an HR diagram. In that HR diagram, basically all it is plotting stars based on the temperature and their brightness or their magnitude. Okay? When you do that, they also kind of arrange themselves in the different colors that are of stars. So, we will be reading one of these, but let's look at the information we can get out of an HR diagram. So an HR diagram is just basically a way to compare stars. And what it does, it basically plots stars by temperature and brightness. And there's four major groups. The first one is what we call stars that are a main sequence. Okay? Stars that are main sequence. Most stars are main sequence stars. The temperature in main sequence stars are related to their brightness. So the brighter they are, the hotter they are. Our sun is a main sequence star. Okay? So for the most part, when we look at main sequence stars, we're looking at stars that are average in age, average in temperature, average in brightness, and so on. Then there's something called giants. Giants, the size determines their brightness. Well, think about it. They're giants. If they're giants, that basically means that they're really big, correct? If they're really big, then aren't they going to be brighter? So, even though giants tend not to be very, very hot, they are brighter because they're very, very big. Supergiants, same thing. Size determines brightness. Because supergiants obviously are bigger than giants. So, once again, even though they're not very hot, because they're so big, they tend to be brighter, their magnitude increases. And then the last one is white dwarfs. So white dwarfs, does that mean that they're big or they're little? They're little. So these are the smallest ones. These are very dim because they're so small. And this is for the most part, because remember, the distance from the observer also has something to do with it. But for the most part, when you think of white dwarfs, they're very dim because they're so small. Because what we'll see is temperature-wise, they tend to be a little hotter. So in an HR diagram, you have these 4 different types or groups of stars. All the stars fit into one or the other. All the stars will fit into each and every one as their life cycle goes on, because the stars change due to the fact that they're burning different elements. So, looking at our 4 major groups, it also allows us to approximate the life cycle stage of a star. So we can see, is it a young star, is it an old star, is it a dying star? Just by looking at where it is in the HR diagram. Most main sequence stars are young to middle-aged stars. So all stars start off as a nebula. So when that nebula has enough gravity to basically pull everything into one area and start going through chemical reactions such as fusion and fission, then what ends up happening, it turns into a main sequence star. So all stars start basically as a nebula, where it's just gas and different particles, and the gravity starts basically pulling everything together. Chemical reactions called fission and fusion occur. It makes a star, and the star becomes a main sequence star. So it's a young star. As time goes by, it goes into middle age, still main sequence star. And then, all this time, it's burning hydrogen. Burning hydrogen, burning hydrogen, burning hydrogen. Then it starts swelling as more of the hydrogen gets burned off. And it swells into a giant and a supergiant. Giant supergiants are basically aging. It's finishing all the hydrogen that it has, and it starts burning the helium that it has. Well, eventually, it's burning most things up, so it dwindles down into a white dwarf. So, a star always starts a nebula, becomes a main sequence, as time goes by, becomes giant, supergiant, and then goes to a white dwarf. Another possibility is that there are chemical reactions that make it explode, becoming a black hole. So it can become a black hole, but we're not going to talk about those very much. Whenever you take an astronomy class, they'll get into that a lot more. Basically, I don't know much about black holes other than they are an area where gravitational pull is pulling everything in. It doesn't allow any light to travel, so we know black holes are out there because there is an absence of light in an area. Yes?
I was reading that with the black holes that in the near future that they're actually going to see it take up the gas cloud and see what happens to it. They said that as it goes toward the black hole, that the gas stretches out and then it goes back to its normal state.
And the better telescopes that we get, and the more our satellites get closer and closer to things like that,
They said that
the more we're going to find out.
they have the technology to be able to see that happen.
That we have the we're going to get.
And we have the technology to see it happen.
And that'd be interesting to look at. Yes?
So what happens if the Earth sun dies into a black hole, but there's already a black hole in the galaxy?
Okay, ask that again.
What happens around us when it tends to...
Around the Earth? Before our sun can become a black hole, it will swell to a supergiant, which means it will engulf the entire solar system. So no planets would be here when that occurs. Because right now the sun is here. It's gonna become this, right? So that means it's bigger. If it's bigger, what happens to gravity? It gets stronger. So if it increases, isn't it gonna pull everything in a lot more stronger? So, basically, most of the planets, and truthfully all of them from what I understand, most or all of the planets will basically be burned up before it even gets to a white dwarf or a black hole stage. Just because, in order for that to occur, the sun has to swell. If it swells, gravity goes up, pulls everything in, burns everything up. Yes, Jesus?
So the white dwarf, it's small, but
Yes.
the size determines the brightness, right? So since it's small and it's a white dwarf, it's hot, but it's not big, so you can't see it as much.
Yes. Which is very counterintuitive. You kind of think, well, it's bright, it should be. But the thing is that
Inside.
there's several things that go into it. Tristan, you had a question?
I forgot which planet it was, but it's like an ice planet. And that planet gets sucked into the sun, but it doesn't make like steam.
It should probably will before it, because don't think that it gets big like it's like here and it gets big and everything goes sucked in. Everything starts moving little by little. Okay, it's a gradual stage. So yes, if it's ice, it would probably start melting before it gets in. Yes.
And how many years is this gonna happen over?
These occur over millions and millions.
And then how do we know who that is?
We know what stars do because we've been able to see stars go through this stage. So because we've been able to see what stars do, and we know what happens when things get bigger and what gravity does and things like that, that's why we know. Not that we've ever seen a star system actually go through that, but we've seen stars go through all these stages and see what happens to the star. So by understanding that as things get bigger, gravity increases, then by logic, the next steps are gonna follow. Yes?
There's a part in our galaxy that they can see on one of the spirals on the Milky Way.
Arms?
These are
I'm
on-
sorry,
on the
hold on,
arms.
because people are talking and they're being disrespectful.
The scientists can see when stars are exploding and turning into like nebulous.
Yes, yes. And and that's how we know that all stars go through life cycle, because we have been able to see that. Alright, any other questions at the end of the notes? Okay, so your assignment is going to actually look at a HR diagram and answer questions. So I need everybody to open up your books to page 153. And remember, there's one for every two people. And take one of these HR diagrams and pass the rest over to your left, and I'll pick up the answers over there on that side.